This is the second part of the lecture series on the derivation of the error formula for Simpson's rule. When we use the quadratic polynomial capital L of x to approximate f of x, f and capital L do pass through the points at x equals minus h, 0, and h. But outside of these 3 points, f and capital L are likely not to coincide. And so the precise relationship between f and capital L is that f of x equals capital L of x plus an error term capital E of x, whose formulation we now have defined. We define a new function g of x, which will be equal to f of x minus L of x, minus a third term, which looks like this. We have the product E of t, where t is different from minus h, 0, and h. E of t is multiplied to the fraction, whose numerator is x squared times the quantity x plus h times the quantity x minus h. The denominator looks very similar, except that we have t squared times the quantity t plus h times the quantity t minus h. We plug in minus h for x and determine the value of g of minus h. On the right side, we have f of minus h minus L of minus h. Now recall that f of x and capital L of x are supposed to be equal at these 3 values of x. And so f of minus h minus L of minus h is 0. Plugging in minus h for x in the third term, more specifically in the numerator, we replace x here by minus h. We get a factor which is equal to 0, so that the numerator and the entire third term of g of minus h is 0. And therefore, g of minus h is 0. As an exercise, one should check that g of 0 and g of h are also equal to 0. So g has 3 zeros in minus h, 0, and h, but there is a fourth 0. We determine the value of g of t by plugging in t for x. The first 2 terms on the right side are f of t and minus L of t. Observe that when we replace x by t in the numerator, and that's the only place where we make the substitution, the fraction is actually equal to 1. And so g of t is f of t minus capital L of t minus E of t. But because of this equation, when x is replaced by t, the right side of g of t is actually equal to 0. So the fourth 0 is at x equals t. At this point in the error derivation, we use Rolle's theorem. Rolle's theorem says that if we have a differentiable function g, and if the y value at x equals r sub 0 happens to be the same as the y value at another x value r sub 1, then there must be a value between r sub 0 and r sub 1, which we call c sub 1, where the tangent to the graph of g is horizontal, or that g prime is equal to 0. We can use the x-intercepts of g to verify the existence of places where there will be horizontal tangents to the graph of g, because the y values of g are identically 0 at these x-intercepts. The function g in our derivation has 4 distinct zeros. Therefore, there must be 3 gaps formed by these 4 zeros, with each gap having at least 1 zero of g prime. As a result, g prime will have at least 3 distinct zeros. These 3 distinct zeros are guaranteed by Rolle's theorem. But there is a fourth 0 whose existence we can confirm. We examine g prime of x, which is f prime of x minus capital L prime of x minus capital E of t times the derivative of this fraction. We only differentiate the numerator since that is the only part of the fraction that depends on x. Check that the derivative of the numerator is equal to 4x cubed minus 2x times h squared. We take advantage of the fact that both the functions f and capital L are even functions. A well-known property of a differentiable function that is even is that its derivative, when evaluated at 0, is equal to 0. Just take a look at the graphs of f and L. If an even function is increasing to the left of x equals 0, then it must decrease to the right of x equals 0 if it is to be symmetric with respect to the y-axis. And so we have a local maximum at x equals 0, and therefore the derivative there will have a value of 0. The argument is almost exactly the same if the function starts out decreasing to the left of x equals 0, in which case it will have to be increasing to the right of x equals 0. So f prime of x and L prime of x are both equal to 0 at x equals 0. Plugging in 0 for x in the third term ends up being equal to 0, and so g prime of 0 is 0. Now x equals 0 is one of the 4 zeros of g that we used to form the gaps where we found the first 3 zeros of g prime. And so x equals 0 is not one of the 3 zeros we had previously confirmed for g prime using Rolle's theorem. So x equals 0 is a fourth zero for g prime, and we now know that g prime has at least 4 zeros. Now applying Rolle's theorem to g prime, Rolle's theorem guarantees that the derivative of g prime, which is g double prime, should have at least 3 zeros. Keeping this up, the derivative of g double prime, which is g triple prime, should have at least 2 zeros. And furthermore, g quadruple prime should have at least 1 zero. Let us call the guaranteed zero of g quadruple prime to be c star, so that g quadruple prime of c star equals 0. Using the formulation of g, we determine g quadruple prime. The first term is simply f quadruple prime. The second term is L quadruple prime, which should be 0, since the fourth derivative of a second-degree polynomial is simply 0. The third term will be the derivative of this product, but we only have to take the derivative of the numerator because everything else has nothing but constants in relation to x. It is an elementary exercise to check that the fourth derivative of the numerator is 4 factorial. Plugging in c star, we obtain a formulation for g quadruple prime of c star. G quadruple prime of c star is supposed to be 0. And so solving for the error quantity E of t is equal to f quadruple prime of c star times the fraction whose numerator is the product of t squared, the quantity t plus h, and the quantity t minus h. The denominator is 4 factorial. If we integrate f of x from minus h to h, this should be equal to the integral of L of x plus the integral of the error term e of x. E of x is given by the last line on the right panel with t replaced by x. We should also remember that the integral of the Lagrange polynomial L of x on the interval from x sub 0 to x sub 2 was the one that yielded the Simpson's rule estimate. So this must be equal to h over 3 times the quantity that starts off with the y value at the first x value, x sub 0, plus 4 times the y value at the middle x value, x sub 1. And finally, we have y sub 2, which is the y value at the x value, x sub 2. This integral must be the error in the Simpson's rule estimate for the first two subintervals, that is the interval from x sub 0 to x sub 2. We designate it as error sub 1 with the subscript 1 indicating that we are using the first two subintervals. We take the absolute value of both sides and still preserve the equation. We bring in the absolute value inside the integral and take the absolute value of each factor. What we get is a quantity that is at least as large as the original quantity. Now c star depends on x, and it is virtually impossible to find c star in terms of x. What we will use instead is the maximum value of f quadruple prime. Now let k sub 1 be the maximum absolute value of f quadruple prime on the interval from x sub 0 to x sub 2, or from minus h to h. We can now bound this part of the integrand by k sub 1.
Because k sub 1 is a constant, we can take it out of the integral. All we need to do now is just take the integral of the absolute value of x squared times the quantity x plus h times the quantity x minus h, all over 4 factorial. By the way, the absolute value of this fraction is the negative of the fraction itself, since x minus h is the only factor in the numerator that is negative. Remember, x is between minus h and h. One can easily check that the integral of this quantity from minus h to h is h to the fifth over 90.
In general, designating capital K sub j to be equal to the maximum of the absolute value of f quadrupled prime on the interval from x sub 2j minus 2 to x sub 2j. Note that the index j for k is half that of the index of this endpoint. Remember, we are taking two subintervals at a time. Then error sub j, which is the error when using Simpson's rule to estimate the integral of f on the jth pair of subintervals, is less than or equal to capital K sub j times h to the fifth over 90. Here, j goes from 1 all the way to n over 2. So the total error then should be less than or equal to the sum of all of these n over 2 bounds. Choosing capital K to be the maximum of all the absolute values of f quadrupled prime on the interval from a to b, each of these k sub j's will be less than or equal to capital K. And so the absolute value of the total error will be less than or equal to capital K times h to the fifth over 90 times n over 2. We multiply the last quantity by n to the fourth over n to the fourth, and use the fact that h is equal to b minus a all over n, or that h times n is equal to b minus a. And so h to the fifth times n to the fifth is equal to the quantity b minus a raised to the fifth power. And so finally, we have the absolute value of the total error, which is equal to the integral of f from a to b minus
The Simpson's rule estimate,
capital S sub n, is less than or equal to capital K, which is the maximum of the absolute value of f quadrupled prime on the interval from a to b, times the quantity b minus a raised to the fifth power, all over 180 times n to the fourth power.